Hi everyone, today I'm going to talk about the Recoil Growth scheme. And so since this is supposed to be a short video, I would strongly recommend you to first take a look at the configurational bias Monte Carlo presentation so you can have a better understanding of how this Recoil Growth technique compares to it. So first I wanted to start with a general idea of how the Recoil Growth algorithm fits into the wide variety of simulation techniques. And so, as we have seen in class, there's some cases where molecular dynamics cannot simply be used to study a system, or perhaps where the natural dynamics of the system are just too slow. And so for this, we saw how the Monte Carlo schemes could be especially useful in these situations because they would allow us to do this very physical trial moves that could kind of help us equilibrate the system. And so there are these cases where, for example, when dealing with complex fluid consisting of chain molecules, so here we're talking about large molecules. In this case, conventional Monte Carlo techniques would also fail because the probability of accepting a random trial insertion is extremely small, and so we would need to make a huge amount of insertion attempts, and it would be so inefficient. And so here's where the bias sampling techniques come into play. And so the main idea is that we bias the sampling to enhance the probability of the molecule that is going to be inserted to fit into the already existing configuration. And so in contrast, the unbiased schemes really don't use information about the existing configuration, at least not for the generation of the trial moves. They use the current configuration, but just to accept or to reject the trial move, not to generate it. And so there are many advantages of doing this, but one thing we need to keep in mind is that by introducing a bias function in the sampling scheme, we're no longer working with a symmetric transition matrix. And so in order to satisfy detailed balance, we need to modify the acceptance rule so that it can compensate for the bias we're introducing in the sampling. And a very popular scheme used for modeling chains in that uses this idea as configurational bias Monte Carlo, of course, and which is already an improvement of the Rosenbluth scheme. And so, following this line of improvements, the Recoil Growth technique, which is the algorithm I will focus on for this presentation, it was developed to try to overcome one of the biggest issues with CBMC, which is the dead alley problem. And so the thing about CBMC is that when generating a new configuration, it looks only one step ahead. And so it might happen that in a given scenario, there would be like no space for an additional monomer to grow on the chain. And it would be completely blocked in all directions. And this is what we call a dead alley. And so at high densities or very long chains, one can easily see how dead alleys would occur more frequently. And so in those cases, of course, configurational bias Monte Carlo, it would be quite inefficient. And so with this idea in mind, Recoil Growth tries to solve this issue by having the possibility of recoiling back a given number of steps and searching for a new open configuration to grow on. And so what it does, it just basically looks several monomers ahead to see whether we could expect traps before actually adding the monomer to the formal new trial confirmation. And so in general, the method goes like this. So first, let's imagine we have L monomers forming a chain. And so first step, of course, if we want to grow a chain like this, is to introduce monomer 1, right? So we would introduce monomer 1 so that it won't overlap with anything else in the box. And then we would go ahead and insert monomer 2 just right next to monomer 1. And we do this because, of course, we're talking about a connected chain. And we see how monomer 2 could be inserted in any of k different trial directions. And so, for example, on a cubic lattice, we would have already k equals 6 possible neighboring spaces to add the next monomer of the chain. But of course, k is a number of trial directions that depends completely on the specific system you're trying to model and the constraints you may have. So now we see that we have k possible chains that could be formed out of all the conformations that we can create for 2 monomers. So we could have k different possibilities. And so if we continue to extend the chain for monomer number 3, each of the K possible dimers we already computed or we already thought about would also have K possible directions where we can insert monomer 3. And so we see that at the end, if we continue up until monomer L, we would have K to the L minus 1 possible conformation, possible branches. And here we're talking about literally all the possible ways we can have connected chains, considering that each monomer has K directions to grow to. But the thing is that most conformations have vanishing Boltzmann factors, and so we simplify the search for the most relevant conformations by introducing the concept of open and closed trial directions. And so I would say that a trial direction for a given monomer J is closed. So for direction B, so let's say here, B could be any of the K equals 4 trial directions. And so if we compute a number and if it is greater than this probability PJV, which is of course the probability of the trial position in the B direction to be open, so if it's greater than or equal than this probability, we would say that the trial direction is closed. If it's lower than this probability, we would say it's open. And we can notice how many of this K to the L minus 1 branches will be closed. So sticking with only the open trial directions really reduces the total search space. And so in general, we would say the algorithm consists of 2 main stages. So in the first stage, we would grow a new chain conformation. And here's where we are computing the energy and the probabilities we just talked about. And then in the second stage, we would compute the weights of the new null conformations. And using the weights and the energies for both stages, we would compute the acceptance rule. And that's how the algorithm works. So for stage 1, each time that we place a monomer, we will be always computing its energy and its probability of being open. And if it turns out to be an open position, well, that's perfect. We just go to the next monomer, even if we don't check the other K minus 1 possible configurations. But if it turns out to be closed, then we will try another trial position. And remember, we just have up to K possible orientations, so there's a chance of having no open trial positions among the K possible configurations. In this case, we would just proceed to the recoil step, and you can imagine how this is basically the essence of the whole algorithm. And here we will first need to define a parameter L max, which is nothing. So this L max is nothing but the number of steps we will go back in the chain in case we're unable to find at least one open trial position. And so, for example, in this illustration, the chain is in a dead alley, so there are no open trial positions for the next monomer. And so the chain will recoil back a number of monomers. So in this case, if this is monomer I, looking for the position of monomer I plus 1, it finds no space. It recoils back to I minus 1, grows again monomer I, and looks for the position of monomer I plus 1, hopefully finding a space that could be useful. And so this L max parameter is user defined, so you can define how many steps you would allow your chain to go back and search for a new configuration. And of course, we can see how this, by changing the number of steps, you can go back the L max steps. We can change or improve our accepted trials. I'm sorry. So once we successfully do this for all monomers, we have already grown the whole chain, and we proceed to stage 2, where we compute the weights of a new and all configurations. And this is the most expensive part of the algorithm, but it is also the part that illustrates how nice recoil growth is compared to configurational bias Monte Carlo, because we're only computing the weights once we know for sure that we have generated a successful trial conformation. And in contrast, in CBMC, we may be spending much of our time on a conformation that could terminate in a dead alley. So this is already an improvement. And so for the new conformation, if we're at monomer I, we have already explored one of all K possibilities. So we have already explored one of the possibilities, which is of course the one included in the new conformation of stage 1. And we might have also explored some of the KC close conformations before passing to a new one. So this is the case where we found it was a close trial position, and then we try with another one. And so we will still have K rust remaining directions we need to test. And so in this case, we would randomly generate K rust trial positions for the next monomer and use the recoil growth algorithm to test if there's at least one segment of length L max that can be grown in that direction. And again, we're not really exploring all possible branches. We're simply checking if there is at least one branch of length L max that could be grown in each of the K rest directions. And if that's the case, we would say that the direction is open, and we would compute the weights using this formula here. So this is for just the weights. And here MI represents the total number of available directions for monomer I, and PI, of course, is the probability that the trial position for monomer I is open. And we would compute the weights like this for all monomers up until L-1 and multiply them to obtain the weight of the entire chain. And so for the all conformation, we will follow a very similar procedure, but instead of considering the K-rest possible conformations, we're really considering K-1 additional directions for every monomer. And so once we have the weights, and because we already have had the energies, we would be able to compute our acceptance criteria using the energies and the weights, right? So for this project in specific, I am building Lennard-Jones chain. So the Lennard-Jones potential is the one I'm going to be using, and computing the end-to-end distance for each chain so that I can study their distribution. In this case, I'm setting the length to L equals 15 monomers. And in addition, I'm comparing also how the number of acceptance trials changes by increasing the number of possible trial directions, which is K, and also how it changes by modifying the number of recoils, the length of the recoil step, and yeah, that'd be it. So thank you so much for your attention, and please don't hesitate to contact me if you would like to talk more about this algorithm.